Find the extremal for the functional y square plus y dash square plus 2y e raised to x into dx. Here we have not been given with boundary conditions. We will just solve Euler's equation and find out the possible expression for extremal. We have capital F equals y square plus y dash square plus 2y e raised to x. We have Fy equals 2y plus 2 e raised to x and Fy dash equals 2y dash. D by dx of Fy dash equals 2y double dash. Thus, Euler's equation can be written as 2y plus 2 e raised to x minus 2y double dash equals 0. 2 is common to every term in the LHS, and when you divide both sides of this equation using 2, you get the equation y plus e raised to x minus y double dash equals 0, which can also be written as y double dash minus y equals e raised to x, which gives us differential equation of second order. We have d square minus 1 into y equals e raised to x, giving us the auxiliary equation m square minus 1 equals 0, which has the roots m equals plus minus 1. Whenever we obtain roots m equals plus minus 1, you can write the complementary function as y equals c1 e raised to x plus c2 e raised to negative x, or c1 cos hx plus c2 sin hx. This is possible because cos hx and sin hx can be expressed as linear combination of functions e raised to x and e raised to negative x. Similarly, you can even write e raised to x and e raised to negative x as linear combination of functions cos hx and sin hx. You can verify whether these functions satisfy the differential equation d square minus y applied on y equals 0. When you consider y equals e raised to x, we have y double dash equals e raised to x, and when you evaluate y double dash minus y, you get answer as 0, from which you can conclude that y equals e raised to x satisfies this differential equation. Hence, y equals e raised to x is a root of this differential equation. Similarly, when you give y equals e raised to negative x, you get y double dash equals e raised to negative x. Thus, we have y double dash minus y equals 0 in this case as well, from which we conclude that y equals e raised to negative x is also a root of this differential equation. If you consider y equals cos hx, you have y double dash equals cos hx, and we have y double dash minus y equals 0 satisfied here as well. Thus, y equals cos hx is also a root of this differential equation. When you consider y equals sin hx, you have y double dash equals sin hx, and here again y double dash minus y is evaluated as 0. Thus, y equals sin hx is also a root of this differential equation. From these equations, it's clear that sin hx and cos hx can be expressed as linear combination of e raised to x and e raised to negative x. Similarly, you can write e raised to x and e raised to negative x also as linear combination of functions sin hx and cos hx. So, either of these expressions are valid whenever you have roots m equals plus minus 1. In this case, we have particular integral obtained as 1 by d square minus 1 applied on RHS e raised to x. Here we have coefficient of x occurring in the function e raised to x is 1. When you give d equals 1, you get the denominator as 0, and hence we have particular integral equals x upon derivative of d square minus 1 applied on e raised to x, which gives us particular integral equals x e raised to x upon 2. Thus we have complete solution y equals complementary function plus particular integral, which gives y equals c1 e raised to x plus c2 e raised to negative x plus x e raised to x upon 2.